and 4.3c part 1, definite integrals and area. Yeah. Okay, so now we're going to actually talk about the actual area, not the approximate area using so many rectangles, which is Riemann sums. This time we're going to use an infinite number of rectangles. So what's going to happen is we're going to let those rectangles get skinnier and skinnier. And I wanted to show you that here. So if you remember, we did this before. Let me do left endpoint, okay? So we're starting at 1. So there's one left endpoint rectangle, okay? Notice there's a lot of underlap, a lot of stuff missing here, and there's a lot of extra stuff here. But if we do 2 rectangles, 3, so what happens as the number of rectangles increases, i.e. the width of each rectangle decreases, notice they're getting skinnier and skinnier, the rectangles, the width along the x-axis. What happens is we get closer and closer to the actual area under the curve. Now, we're only at 20 at this point, and look at how much better these approximations are. There's still a little overlap and a little underlap, but as we increase and increase and increase, those overlaps and underlaps are going to disappear. And eventually when we get to 80, let's see if I can fast forward this. I'd like to try. And let's just make the value 70. Okay, so notice at this point we're at 73 rectangles, 74 rectangles. There's a tiny bit of overlap here, but very minuscule, and the more and more we go, the more it disappears. Okay, so stop. All right. So basically what happens if we let the number of rectangles go to infinity, okay, so the limit as n goes to infinity, n being the number of rectangles, then if we take the width of each rectangle, which is the delta x, which of course now is getting tinier and tinier and tinier, times the sum of the heights. What I'm doing here is adding up, it's like the Riemann sum, I'm adding up the areas of all the rectangles. That's the common width of each rectangle, and this is the sum of the heights of the rectangles. And what happens is that very ugly expression has been reduced down to what we call the definite integral from x equals a to x equals b, where x equals a and x equals b are the left and right borders of the shaded region, and where the width of each rectangle is dx, which is that tiny little, width of each rectangle, and then the s represents the sum, because it's the summation notation, sigma, s for sum, sigma, and then times the height. And the heights, of course, are going to be different depending on where you are. Here, the height is not as high. Here, it's very high. Here, it's a lot lower. But what you're doing is adding up all those rectangles. Now, it is equal to this as long as your function f of x is positive for all x between a and b. In other words, the graph has to be above the x-axis for this exact integral to be the area. Okay, so this is very simple. If you're given a picture like this, you're told this is y equals x squared. It's identified the left border is x equals 1, the right border is x equals 5. You can visually see your function y equals x squared is the top border, and you can visually see the bottom border is the x-axis. Then the area of that shaded region is exactly equal to the integral from x equals 1 to x equals 5 of the function f of x, which is x squared in our case, dx. Okay? Now, I'm saying eventually, you guys, I can erase that now because you already know how to evaluate a definite integral. And as you know, we integrate the x squared, we get x cubed over 3, and then we evaluate that from 1 to 5. Remember, first we plug in the top limit of integration, which is 5, and then minus, and then we replace x by 1, which is the lower limit of integration. Turns out the exact area of that region is 41 1/3. Okay, we've seen this before, the first fundamental theorem of calculus, and that's how to evaluate a definite integral. So here's another example from 1 to 2 of x squared dx, etc., etc. And as long as your function is above the x-axis, then the area of the region bounded by that function, the x-axis, x equals a and x equals b, that area is exactly the definite integral from a to b of f of x dx. Okay, so basically when you're looking at the expression, because they're going to have you work backwards from the definite integral to the actual diagram, the lower limit of integration really is your left border. X equals that number is your left border. Your right border is x equals b. Your top border is f of x. And your bottom border is the x-axis. Okay? Okay, so on page 278, 13 to 22, set up a definite integral that yields the area of the region. At this point, they don't want you to evaluate the integral. They just want you to be able to go from the diagram to the definite integral that represents the area of the shaded region. So again, you just have to figure out left border, right border, top border, bottom border. Notice the bottom border is the x-axis. That's good because that's all we know how to do right now. The left border, as you can see, is the y-axis, which is the vertical line x equals 0. The right border, the furthest to the right the shaded region goes, is at x equals 2. And the top, of course, is the function they gave you, which is 4 minus 2x. Hence, the area is exactly equal to the integral from 0 to 2 of 4 minus 2x dx. Very, very, very simple to do. Okay, here's number 20. This time the function is y equals tan x. As you can see, the left border is x equals 0. The right border is x equals pi over 4. Tan x is our top border. X-axis is our bottom border. And therefore, it's equal to this integral. Okay, now, so far, we've been looking at things thinking of breaking them up into little vertical rectangles where the width, that common width of each rectangle is along the x-axis. Notice also all of our functions have been in terms of x, and the dx tells you that these are little subdivisions down here of dx between each value and the next x value. Also, the left and right borders were identified by the lower and upper limits of integration because they represented x equals a, x equals b. So everything we've done so far is in terms of x. Okay? Now, what we're going to do is we're going to tilt our heads, and now we're going to do it in terms of y. So here's how that works. If it's in terms of y, first of all, it's going to have to be dy. The function's going to have to be in terms of y. And the lower and upper limits of integration are not going to represent vertical lines x equals to x equals. They're now going to represent horizontal lines, y equals to y equals. So now what happens is this no longer represents the left border because that's x equals a. It represents the bottom border, which is y equals c. Up on top, you have the top border, the horizontal line y equals d. The right border, instead of the top border, the right border is now your x equals f of y, and your left border is now the y-axis instead of your bottom border being the x-axis. Okay, so it's all switched around. So basically, this picture would represent the integral from bottom border y equals 0 to top border y equals 2 of right border x equals y minus 2 all squared dy. Okay, so bottom to top, which is y equals 0 to y equals 2. Make sure you use the y coordinates of those points. And then right border minus y-axis. So it'll be the y-axis for now. Okay, all right.